So let's now take a look at the naming of molecules, which is given the term nomenclature. It was originally developed by a man named Alfred Stock in the 1919, and he based the system strictly on the inorganic compounds, meaning it didn't contain carbon. And that set of rules that you created is still used today. Later, in 1921, the system was expanded to apply to any compound of any kind. You can divide the elements and compounds and molecules in the following way. You can have a pure substance, which means you have only one kind of element. And that one kind of element can appear alone, such as neon, or a one kind of element can bond to itself, such as oxygen, and make a molecule of two of its same kind. And then you have a compound. Again, compounds come in two types. One type is referred to as a molecular compound. In a molecular compound, the atoms are covalently bonded together. That's when the electrons are being shared. It's a very strong bond. Molecules tend to hang together very, very well. And the other kind is an ionic compound. In that case, the atoms are linked together due to ionic or electrostatic attraction. Pluses, minuses, cations, anions are attracted to each other. And what you tend to get are these very large blocks of repeating atoms connected to each other because of these charges. And these, to name them, we use the formula unit or smallest unit that contains the atoms that are connected. When you have, for example, propane, CH3H8, that's an example of a molecule. Whereas if you have NaCl, that's ionic, because of the ion attracting. A ionic compound is referred to as a salt. We, of course, know table salt is NaCl, but that's not the only kind of salt. The word salt applies to ionic compounds. Now, to make the naming system work, you must keep this straight. When you look at the periodic table, all the atoms in the first column are a +1. That is because the outer valence shell has only one electron, which it loses, thereby assuming a positive charge. Of course, if you look in the second column, beryllium, magnesium, calcium, if you looked at the outside valence shell for those atoms, they lose those two electrons to become stable, giving them a +2 charge. On the right side, fluorine, chlorine, bromine, they all have 7 electrons on the outside, and they're going to acquire an extra electron to complete it, giving it a negative charge. And the argument applies to the column with oxygen and the column with nitrogen. A couple items, which is the column containing carbon and silicon, they have 4 electrons in the outside valence shell, and on occasion they will either drop all 4 or gain all 4. However, as a general rule, they do not take that approach. Instead, they typically become covalently bonded and do not go the ion approach. On the far right, those are our noble gases. Their outer valence shell is already complete. Therefore, they are completely unreactive since they've achieved stability. Notice finally that hydrogen appears on the top of the left column above lithium. It also appears on the right side above fluorine. That is because at times hydrogen can pick up an electron, becoming negative, although it most common dumps it, becoming a plus charge, which is what you see on the left side. The other really important idea before we get into the naming of compounds is to know these broad areas or groups in the periodic table. You'll notice the tan color, those atoms are all metals. And they're called metals because they all lose electrons and assume a positive charge. The green atoms on the right of the periodic table, those are the nonmetals, and they will tend to gain electrons to complete the outer shell, and therefore they will tend to become negatively charged ions called anions. And finally we have in purple the semi-metals, also called the metalloids, which I consider the best name for a heavy metal band, if you're into that. But the purple, they tend to display both properties of the metals and non-metals and can show characteristics of both. We do not tend to work with them in the naming process, but you do need to recognize them. And notice the staircase where the metalloids or semi-metals appear. That is considered the dividing line between the metals and the non-metals. And these are things you should absolutely commit to memory and should be very almost automatic. When you see these, it will help the naming process a lot. So when we go through this naming, I created numbered categories. These category numbers are not part of the normal accepted names within the scientific community, but it does help me to teach the nomenclature to students. So this is what I call a category 1, which is a metal to a non-metal. You notice an example is the chlorine and the sodium, which form a very, very regular lattice work, and the right side picture shows you the actual crystal, which is what this is. How do we give it a name? To name a metal to non-metal, here is our example. Lithium is a non-metal. Phospholide is the non-metal. And lithium is a +1 because it's in the first column. And phosphorus is a -3. It is a non-metal. Now, when you form a compound or a molecule, the overall charge of that compound overall must be neutral. So when lithium and phosphorus link up, you'll notice there's a +1 and a -3. So when they associate, you do not have a balance of ions to make the compound. So what happens is 3 lithium become associated with the single phosphorus, and you get Li3P. The subscript 3 indicates that there are 3 lithium atoms for every phosphate atom. Let's take a look at calcium nitride. When you see calcium, it's in the first column, the second column. So that's a Ca, it's a +2 charge. It is a cation. And then the nitride is the anion. It's a non-metal. It's gained 3. Now, again, if they link up, it's not neutral overall. And so what happens is you have to pick up extra numbers in order to balance them out. Now, a very important idea here is look at phosphide and nitride. Notice the IDE ending. The IDE ending means it is a single atom, it is a anion, and it is a flag to let you know you're looking at a phosphorus or a nitrogen atom. Because you will in the future see names such as phosphate, phosphite, nitrate, nitrite, and when you hear those endings, it means a different item. And the IDE is letting you know that it's a single atom that is involved here. So those are how you name a metal and a non-metal. Notice that, again, we bond them together. It forms a salt. That the ending compound has to be neutral. The cations, which are positive, a helpful way to remember that is when you spell cation, the T looks like a plus, so that must be the positive. So the cations and the anions, they have to be in a ratio that gives you that neutral charge overall. And be aware that when you do write that out, that's referred to as formula units. They're not true molecules, because what happens is these ions string together in these very, very large structures. What you write down is the smallest unit of that the actual compound. Now, as we just saw, you want to write the name of the cation or metal first. You will use the needed charges to balance that out. And then you write the names of the anions or nonmetals. And again, you will change the name of that ion to indicate it. And finally, when you put them together, the overall charge has to be 0. Now comes what I refer to as a category 2. And in category 2, you have transition metals to nonmetals. It would be to your advantage now to look at your periodic table and notice that the transition metals sit in the middle of the periodic table, and it has the items that we traditionally associate with being metals, such as nickel, such as titanium and copper and iron, etc. Those are all transition metals. Now, what makes them different is transition metals sometimes can achieve two different ion states. For example, mercury can achieve a +1 or a +2 state. So if we have iron and we have bromate 3, you'll notice that iron can have two different states. Iron can be a +2 or it can be a +3. How are you supposed to know if iron's a +2 or a +3, or perhaps iron might be a +1 and a +4? How do you know which are your choices that iron can assume? If you look at the polyatomic chart, which is a separate listing, it will indicate to you what are the options, what are the possibilities of these different transition metals, and what the different charges are that they can assume. So we're wondering, which one is this going to be? And what you'll notice is that the bromate is 3, and so there are 3 minus charges here. Therefore, the formula unit written down has only 1 iron. So it must be in the +3 state, because that is the only way to balance with the -3 anion. And so that's the one that the iron is in. Therefore, you write down iron 3 bromate. Notice that the Roman numeral 3 after the word iron, it's indicating what is the ionic state that ion is in to balance it out. There's a third category of ion called a polyatomic ion. Let's take strontium hydroxide. Strontium, which is in the second column, Sr, it's a +2. So it's going to bind with a combination of OH. Now, OH is hydroxide. The oxygen and the hydrogen are not held together by ionic charges. Sometimes oxygen can be a -2, hydrogen can be a +1. That's true. But in this given instant, the oxygen is covalently bonded to the hydrogen, and therefore the OH is a working molecule. Now, along the way, the hydroxide picks up an extra electron. So the OH molecule itself is a -1. And what's going to happen here is strontium is going to bond with the O hydroxide molecule. Now, our tendency or habit is to say, right, if I have a +2 strontium and hydroxide is a -1, I need 2 hydroxides. So one tends to put a 2 as a subscript. And of course, strontium have 1. And the result is SrOH2. But that's not right. You can't write it that way. And that's because the way it's written right now is it says there's 1 strontium, 1 oxygen, and 2 hydrogen. That's not what we're saying. What we're saying is there's 1 strontium and there are 2 hydroxide molecules. Now, the hydroxide, or OH, that molecule is called a polyatomic ion. It's called polyatomic because there are 2 or more atoms that have come together to form a molecule, but it has a charge, and therefore it's an ion. To further complicate things, you need to recognize that although OH hydroxide is a molecule, it's engaging in a ionic bonding with the strontium, and it's based strictly upon charges. Now let's take another example of polyatomic ions. For example, can 2 polyatomics link up? Absolutely. In this case, you have ammonium, which is a +1, and you have a phosphate. Sorry, let's back that up a little bit. The phosphate is a -3. The ammonium is a +1, so I need 3 ammoniums to balance with the single phosphate to make an overall neutral compound. Now the question sometimes comes up, which is, how am I supposed to recognize that I have a polyatomic situation and not just say a metal and nonmetal? A compound is a polyatomic situation if there are 3 or more different kinds of atoms involved. Let me back it up here and try to show that to you. You'll notice in the green box SrOH2. Now, how is one supposed to know that you have a polyatomic? Well, you'll notice that there are 3 different kinds of atoms: strontium, oxygen, hydrogen. At that point, you realize there has to be a polyatomic molecule in there somewhere. Here, of course, you have the 2 polyatomics together. Now, what I'd like you to do at this time is I'd like you to practice and write down the formulas for the following ionic compound. You can pause this for a moment and try to work those out. I will be able to show you the answer in just a moment. So pause it and take a look. When you get a chance, you can pause again and work on numbers 3 and 4. And there you have your answers. Category 4 are nonmetal to nonmetal. Water is an example of a category 4 molecule. This type of nonmetal and nonmetal share electrons. The bonds that are involved are covalent bonds. That means that they share electrons in order to complete the outside valence shells. They form molecules. If you have a hydrogen in the front of the formula, it's not going to be a covalent compound. And if you have ammonium NH4, it's again not covalent. And here are some examples. So you do need to recognize that there are exceptions to the nonmetal to nonmetal. So let's take a look how this works. The challenge in these names is that nonmetal and nonmetal are covalent. They share electrons. And because they share them, they don't form charges. And if you don't have ionic charges, you can't figure out how many of each kind of atom are involved. Take carbon dioxide, for example. The carbon is not going to assume a charge. The oxygen is not going to assume a charge, which often can be a -2. These atoms are sharing electrons. There's no charge. So there's no way of figuring out how many of each kind of atom you need. Therefore, what you do is you add prefixes. So carbon dioxygen is what you would have. You would shorten it to dioxide. Nitrogen, which is a nonmetal, is covalently bonded to chlorine, which is a nonmetal, and you use di and tetra to designate how many of each kind of atom. And you shorten it to tetrachloride. To help us along, here are the prefixes that you need to know in order to name the different nonmetal to nonmetals. Here are some samples to work through. I've given you the first one. Try to solve the second and the third. You can pause it now perhaps and go the other direction, figuring out what the formula is for these molecules. Now, there are some special cases when it comes to nonmetal to nonmetal molecules. And what they are is some molecules are given almost nicknames. And they don't follow the rule because they're used so common in the general public. So NH3 is not going to be ammonia trihydride. Instead, it's simply nitrogen trihydride. It's simply given the name of ammonia. This molecule, which is CH4, is methane. One might have assumed it could have been carbon tetrahydride, which is correct, but what we refer to it as is simply methane. This is acetylene, which is used in acetylene torches that are very, very hot. And this is referred to as benzene, which is actually a very dangerous chemical. So these are common names used rather than the technical terms. At this time, how about making an effort to write these names as practice in the ionic compound, looking at the different rules. I'd like to point out in number 2, you'll notice 10 Roman numeral 4 oxalate and stannic oxalate. 10 can use either version. many years ago, there were no Roman numerals used. It was ich and us used to denote what was the charge. They have since moved towards the Roman numeral, but you still see those, and either one is acceptable. Acids is the fifth and final category to work with. The naming of acids, the hydrogen is written first, and there are two groups of acids. One is the binary, and the other one is the oxyacids, which contains the oxygen. So let's take a look at how you go about naming these two groups. The oxyacids, which you see there, HClO3, as opposed to the HCl. When it comes to the binary acids, remember that's the one without the oxygen, there are two categories. If the acid powder is dissolved in water, it's referred to as an aqueous solution and is denoted by being AQ. That is something you will need to recognize and know. When you name an acid that is in aqueous state, you begin by writing hydro, and you simply name the next element with a ic ending. Sulfur becomes sulfuric, phosphorus becomes phosphoric. And you simply tack on the word acid in the end. But what if it's not dissolved in water? What if it exists as simply solid in a powder? Even though it's the same material, but because it's not in water, you write the word hydrogen and simply the name of the second element. And as before, like we did with the ionics, we simply add IDE. So here we go. You have H2S. Now there's an error because it's written as G. It actually should be S because it's a solid. So H2S in a solid form is hydrogen sulfide. And that exists as a solid powder. But if you take that powder and dissolve it in water, now it's an aqueous acid. Now you call it hydrosulfur. So if you hydrosulfuric, and you add the acid name on. So it's the same material, just one is dissolved in water, the other one is not. How about the oxyacids? Well, you write the name of the anion, change the ending. If the anion is 8, it becomes ic. If it becomes ite, it becomes us. And then you add acid to it. So HClO3, and again, what I'd like to emphasize, when you see a written formula, if it starts with an H, it immediately tells you I'm dealing with an acid. So that is your flag to know what you're working with. So ClO3 is a chlorate. It's a polyatomic if you look it up on the polyatomic chart. We're going to change that to chloric, and we simply say acid. Notice it's an aqueous state. HNO2, NO2 is nitrite, nitrous acid. Take a moment, pause it, and work through these different naming systems for acids. Pause it and take a look. There you have it. There you go. Hope that was helpful.